Okay, good morning. I just want to try to finish up our little packet of notes that I gave you yesterday, and that way you can finish up the questions as your hybrid work today. We got all the way yesterday through working with wavelength. I couldn't remember if I know I had given you the formula. I know we talked about the formula, but I wanted to talk a little bit more about frequency, how frequency means cycles per second. And I know I said it, but I don't know if we wrote it down. I personally prefer to use hertz because it means cycles per second, which is like waves per second. But you can also see frequency with the numerical value, and then it will just say per seconds. Or another way you might see it is the numerical value with seconds to the -1, because we understand seconds to the -1 means per second. So those are three different ways you may see frequency within a problem. Everything we've gone through so far talks about waves or applies to light as it moves like waves. However, light also contains a great deal of radiant energy that has other properties other than the properties of waves. So we have the wave model that doesn't explain some of the behaviors of light. It explains some, but not all. So we have to look a little bit farther. So three of the things that are really important to understand about how electromagnetic radiation and atoms interact. And I'm just going to kind of go through these quickly, and then you can start and stop the video as you choose. The first one that we couldn't really explain completely with the wave model was the emission of light from hot objects. And I know I just barely touched on that yesterday, but that emission from light from hot objects as they continue to heat and heat, we know that the color of light shifts, but the fact that it's not colored before we heat it makes us call that black body radiation. You have to think about how an object appears before it's heated and how it appears during heating and at the very end when you decide to stop heating. From that, maybe if you have something like a nail or a horseshoe, I think I talked about yesterday, as you continue to increase the intensity of heat, we change the intensity of light emitted. And if you look at the back of this, I hope, I put in just a simple picture of, I don't think I put in the picture of the horseshoe or the nail, but I think you've got that picture in your head. I did put a picture of a nail at the back, I believe, that shows the photoelectric effect, if I'm remembering correctly. Photoelectric effect, you should have talked about it in Chem 1. I know we do now, but it's simply the emission of electrons from a metal surface on which light shines. And you can see it, I'm sitting here in the room and I'm looking over at the gas jets in the faucet. Light striking it, the metal's really shiny, really luminous. As I increase the intensity of the light, I increase the intensity of electron emission, which explains kind of the difference in luster of some metals compared to others. And then the third one is the emission of light from electronically excited atoms. And that has to do with both the intensity of the heat source supplied, but also it deals with the emission of the light. I talked about your flame test that you should slightly remember doing, which we're going to repeat this year and have you make the solutions and the various molarities and several other things with them. But when we look at that, we see a definite color of light. When we look at it through a spectroscope, we'll see its actual line segments that fit into the values of electromagnetic radiation. So emission from electronically excited atoms. Notice this electronically could also just mean application of energy. When we say that electronically, we're talking about the electrons having some source of energy supplied to cause movement. So those are your three different things we have to talk about there. And I wanted to just hit each one just a little bit harder. The first one I talked about was that black body radiation. Yesterday I mentioned that stove burner and horseshoe, tungsten light bulb, if you've ever seen one of those, that's another. And this black body radiation, by moving on and learning more about light, it helps us understand the relationship between temperature and light intensity. We know that as we increase temperature, the intensity of light emitted by the object increases. Think about that, Roy G. Biv, and how it changes: red, orangey hot, yellow, and if you heat something enough, you can get all the way to the end of the spectrum, that is that blue-violet spectrum. So, something to think about. Also here, before we go any further and into photoelectric effect and those kind of things, I want to talk a little bit about Max Planck. Max Planck started working on this in the early 1900s, and he was able to start to find a relationship that had to do with energy and light. And he labeled energy as E, and what he said was it could be absorbed by an atom in definite chunks of some minimum size, depending upon the atom, of course. That tells us the size, and depending upon where electrons are in the atom, that tells us the size. But he called it chunks, and then later, as he studied further, he began to call these chunks quantums of light. So he coined the term quantum, which is where our quantum theory comes from, or quantum mechanical theory comes from. Quantum,
I didn't get that.
quantum you should have heard before. Quantum is actually, and this is a little confusing, I think it seems backwards, but anyhow, quantum means a fixed amount. An individual quantum, that's singular. If you're talking about multiple quantums, then you call it quanta. And it's just simply a fixed amount of energy, so it's measured in joules. The smallest quantity of energy that can be released or absorbed as electromagnetic radiation. That's your quantum of energy. Planck continued to study with various elements, various tests and experiments, and he came up with Planck's constant, that's an H, which is the energy of a single quantum. This is a constant. It's something you should know, or if you don't know, you should get it back in your brain. 6.626 times 10 to the negative 34th joules times seconds. That's a 4. And it's joules. It's just joules. Joule seconds is how you would say that. He further said that matter only consists of whole quantums. For example, you could have 3 quanta of energy. You wouldn't have 3.5. So it's always a whole number. When a quantum is released, you release a whole quantum. Because energy can only be released in those specific amounts, we actually say that this energy is quantized. So that's another word. So energy, when we're dealing with this theory and this application to light, a movement of electrons, that energy is called quantized energy due to the quantum nature of it. Planck, all of this work was so groundbreaking that he won a Nobel Prize in 1918. So then we move on. Go a little further, talking about light being quantized, and get a little bit more specific with things. Sorry, having trouble with my papers here this morning. So after Planck came up with all of these things, we started further experimentations by other people in the 1900s, and we found the photoelectric effect. Or we had the photoelectric effect, I guess. Planck came up with it, but he didn't really understand how it worked. He had started to plot it out, and along comes Einstein, who we've talked a little bit about before in his additions to the quantum mechanical theory and the time-space continuum and all of those things. So Einstein looks at this light that strikes a surface, and he says it's like a stream of tiny energy packets. He calls each packet, or he says that each packet is like a particle, like a quantum, and he called each particle of energy a photon. So that's the second introduction of a new word. So quantum, quanta, quantized, photon, but he begins to call these particles of energy, each little packet that's released or absorbed, this particle of energy, he begins to call them photons. He does further work, and he extends Planck's quantum theory. He says that the energy of a photon is equal to whatever that energy is in joules, times Planck's constant, times the frequency of travel of that energy, which we talked yesterday about that being the Greek letter nu, and there again are your three choices for units on that. As we look a little further, there's kind of a lot written down here. He also says that radiant energy is quantized, and under the right condition, if a photon strikes that metal surface, then it has the ability to transfer that energy into the metal. Each type of metal, if I think about all the metals on the periodic table, each type of metal needs a specific amount of energy in order to have that electron jump and emit that light. The minimum energy that's needed, Einstein called that work function. And he says that it's the energy that's required to overcome the attractive forces that are within the atom. Remember those attractive forces between the proton and the electron that holds the electron in a set path. Well, he said there's a certain amount of energy that's needed to remove that electron or to cause that electron to jump and therefore create the shine. If there's enough energy, the electron can overcome the work function, and if there's not enough energy, then no extra light will be emitted. And we can see that when we look at things like calcium under just a normal light source. If we change the amount of energy and we get it high enough, then we're able to cause that atom to move, or I'm sorry, I should say the electron to be change its place within the atom or be emitted from the atom. So you have to look at your numbers, your energy that's required, to see if you can overcome that work function, to see if the whole thing will actually play with that particular atom or that particular elements of those electrons of those atoms. Einstein, for his addition and all this work on the photoelectric effect, he won a Nobel Peace Prize in 1921, I believe it was, for his work with quantized light and coming up with the term photon and being able to apply it to metals. I'm seeing what I have under here. There's that picture, one of them that I was talking about. I think we looked at a couple others yesterday. That should give you enough information. You are going to have to use, I believe, in the rest of those problems, this E equals HV, and it's going to talk to you, or the problems are going to ask you about the minimum amount of energy required when they do that, or it may ask you for a certain frequency of light and give you an energy. Then that should clue you in that you're using this E equals HV. Do remember, and I can't remember if I gave you any, I'd have to pull the book out and look, but there are times when you have to use C equals lambda nu and E equals H nu. Use one or the other to solve for nu or frequency, and then you have to plug it into the other one to perhaps find something that you're needing. So remember, and honestly, I'm sorry, I should have looked before I started, but sometimes you may have to use both formulas in order to solve one problem. Okay, that's it. I hope you guys have a great day. Just be sure you get these and finish up those. I don't know, there weren't very many problems left besides what I gave you yesterday. And then on Friday we will be able to spend some time and build our spectroscopes and go from there. Talk to you later. Have a good day.